During the debates between Albert Einstein and Niels Bohr about the interpretation of quantum physics, Einstein famously said that God does not throw dice. In this statement, Einstein was not expressing a belief in God, but expressing his rejection of the idea that the universe can be intrinsically probabilistic. An intrinsically probabilistic universe, as is described by the most popular interpretations of quantum mechanics, is incompatible with Einstein's theory of relativity. In Einstein's general theory of relativity, the universe consists of a curved four-dimensional space-time, where time is just another dimension, similar to the three spatial dimensions. In fact, we can describe our universe using any four-dimensional coordinate system we wish, even with none of the four coordinates corresponding to the time dimension of any observer. According to Einstein, our four-dimensional universe can be thought of as a single block, and the passage of time is merely a psychological illusion to beings such as ourselves. A hypothetical observer outside our block universe would simultaneously see all the past and future versions of ourselves throughout our entire timeline. The present version of ourselves would be no more special than any of the past or future versions of ourselves. Just as there are no special positions in space, there is also no special moment in time. This idea is essential to Einstein's theory of relativity, which states there is no special moment in time called the present. This is because different observers inside our universe will disagree on whether or not two events happened simultaneously. Even after we take into account the amount of time necessary for light to reach our eyes, different observers can still disagree on the simultaneity of different events. There is no universal moment in time called the present that all observers can simultaneously agree upon. Just as different observers can have different orientations for the three axes for the three spatial coordinates, different observers will also have different orientations for the time axis. When selecting a new space-time coordinate system by rotating the axes, the axis for the time dimension rotates in the opposite direction of the three spatial dimensions. Therefore, even in the theory of relativity, the time dimension is special in that it is not exactly like the three spatial dimensions. But the key point is that there is no special point along the time dimension which we call the present, and this leads to the idea of a four-dimensional block universe. However, this idea of a four-dimensional block universe is shattered if we believe that the universe is intrinsically probabilistic, as is stated by the most popular interpretations of quantum mechanics. When we say that the universe is intrinsically probabilistic, this means more than simply that it's impossible for us to predict the future. This means that it's impossible even for an observer external to our universe to predict the future, because the future doesn't yet exist. To understand this, let's first consider the scenario of traditional determinism. Suppose we have a sequence of numbers as a function of time. Suppose there is a pattern to these numbers, so that if you know the number at any one point in time, you can extrapolate forward to predict the numbers in this sequence at any future moments in time. This is analogous to the universe as was described by the classical laws of Newtonian physics, and to the universe as is described by Einstein's theory of relativity. Now, let's again suppose that we have a sequence of numbers as a function of time, but this time without any predictable pattern. Even if we know all the previous numbers in the sequence, this is not enough to be able to predict any of the future numbers. The existence of such a sequence of numbers does not yet shatter the idea of a block universe. A sequence of numbers without any pattern could still exist inside a block universe. An observer outside this block universe would be able to see the entire sequence simultaneously. Hence, all the numbers in the sequence can be thought of as always having already existed from the beginning, despite the fact that we humans are not able to predict them. But this is not what an intrinsically probabilistic universe means in the context of quantum mechanics. It literally means that at any given moment in time, the future numbers in this sequence don't yet exist. In other words, the future numbers are not knowable even to the hypothetical observer outside the universe. This shatters the very notion of a block universe, since the block universe theory states the entire timeline has always existed from the beginning, and an external observer would be able to see it. The idea that even an observer external to our universe would not be able to predict the future is not merely a metaphysical supposition. There are empirical observations and scientific experiments we can make which address this issue. Consider, for example, the spins of an entangled pair of particles. In classical physics, the spin of a particle can be described by an arrow pointing along the axis of rotation. Particles spinning in opposite directions will have their arrows pointed in opposite directions. In quantum mechanics, we can only measure the spin along one axis at a time. We will refer to the results as either pointing towards the red plate or pointing towards the blue plate. In our pair of entangled particles, suppose we measure the spin of each particle only once. If we measure the spins of our two entangled particles along the same axis, the two particles will measure opposite spins 100% of the time. If we measure the spin of one particle along the x-axis, and we measure the spin of its partner along the y-axis, the two particles will measure opposite spins 50% of the time. These facts are not mysterious. What is mysterious is what happens when one of the two detectors is oriented in the diagonal configuration, offset by 45 degrees from the other detector. In this case, the two particles measure opposite spins approximately 85% of the time. This result has been experimentally verified many times. Many physicists view this result as evidence that the future cannot be predicted, even by an observer external to our universe. The reason for this is explained by the following. The letter D represents the diagonal axis. Hypothetically, suppose an observer external to our universe could predict all future measurements of the spin states for all possible future orientations of the two detectors. Let's graphically illustrate these predictions for each set of entangled particles. Here, we show an example where the spin of a particle along the diagonal axis is opposite to the spin of its partner along the x-axis 85% of the time, and opposite to the spin of its partner along the y-axis 85% of the time. The problem is that there is no way that this can happen 85% of the time while still meeting all the other conditions specified. For example, one of the conditions specified was that if we measure the spin of one particle along the x-axis and we measure the spin of its partner along the y-axis, the two particles will measure opposite spins 50% of the time. This is not the case in this illustration. As can be seen in this illustration, meeting 50% correlation between the x-axis and the y-axis is impossible if we want to also meet the 85% value regarding the diagonal axis. The problem with this illustration is that it assumes that the spin of a particle along each axis can actually be predicted by some hypothetical observer. Suppose we eliminate this assumption. Suppose that the future does not yet exist, and that the future spin states are therefore impossible to predict, even by an observer external to our universe. Since we only measure the spin of each particle along only one axis, there is no need to create an illustration such as this one. If there are no predictable measurements to the axes which we did not measure, and we focus only on the axis for each particle which we actually do measure, the paradox goes away, and there are no longer any contradictions. The fact that we measure the 85% value regarding the diagonal axis is what leads many physicists to conclude that the value for the spin of a particle doesn't actually exist until the measurement is actually made. Hence, this leads to the more general conclusion that there are certain properties of particles that don't exist until they are measured. Another way of stating this is that the future value of a measurement doesn't exist until the measurement is actually made. The idea of the future not yet existing shatters the view of the four-dimensional block universe, which states that the entire timeline has always existed from the beginning. It is possible to try to reconcile quantum mechanics with the idea of a four-dimensional block universe. But this involves delving into various other interpretations of quantum mechanics, as discussed in detail in the video titled Quantum Physics: List of Philosophical Interpretations. Also, a much more detailed explanation of the 85% value regarding the diagonal axis and its implications is available in the video Quantum Entanglement, Bell Inequality, EPR Paradox. Special thanks to everyone supporting us on Patreon. Your support is very much appreciated.